Hello friends, welcome to our channel. Let's look at this problem, split and merge array transformation. So in this video, we're going to analyze how to use breadth-first based search to do this problem. So here I'm going to do two things. First, I'm quickly go over the problem statement and why it hints us to do BFS, right? And then we do the coding. And in the coding, we are going to explain the data structure corresponding to BFS, that is a queue, right? So later we do some test. So first, we are given two arrays, nums1 and nums2. Actually, I changed them to be A and B just for convenience. So we may perform the following split and merge operation on nums1 any number of times. So we can choose a subarray, right? And then we can take out from the original list and then put in any position, right? So we want to return the minimum number of split and merge operations needed to transform the first list to the second one. So here there are two examples. So the first examples, you can choose this one and put it in the beginning, or relatively you can choose this one and put it into the end, right? That's the one. So in the second one, it has a detailed explanation to get the minimal operations. So let's look at the constraints. First, so this one is very important because it determines the problem size. So here the two arrays at the most has length 6, right? So the numbers can be negative, can be positive, can be 0 within this bound. And the nums2 is a permutation of nums1. So this is a consistency assumption. First, let's see why we should think of BFS. Here's one. Return the minimum number of split and merge operations. So you can start from this nums1 or A as the beginning state and then go to this state, right? So you can formulate them or understand them as a shortest path problem. So you can use BFS. You can also think of Dijkstra's algorithm. For this problem, we can do BFS. But from one state to the go to one and use one operation. So we have many states. But here, the first constraint restricts the total number of states because it's so small. We can consider all the possible states. So this is the exact hint, right? So for example, for each state, you generate all possible successors, right? And then we can do the traversal again. So this will be the full thoughts. So now, once you digest the problem, you can see the BFS. So you can think of the BFS is reading out from the original state through the number of operations, that is split and merge, right? So once you get the final state, you just stop. So here in the example 1, from this state, you can have this state, those states, right? And so on. This one is the goal, right? So we just need one step. Therefore, the return is 1. So before I go to the coding, I want to mention some knowledge point. So this is for iterative implementation of BFS or DFS, right? So for BFS, so we know that we are going to use queue data structure. For DFS, we are going to use a stack data structure. So this is very important to notice, right? So with that said, we can do the coding. So in between, you are going to digest the final details. First, in order to avoid repetition, so I get this set. Then I'm going to initialize a queue. So here I'm going to use collections deck. So here deck, you can pop from left and append from right. So this way you mimic the queue behavior, right? So first, I'm going to add the original state. So this will be, so you can do something like this, right? So you can also add the original list and 0. So because this is the status, this is the number of operations we need, right? So then here visited, so we can add, so this is the set. So because for a set we need something immutable or hashable, so we can add tuple of this A, right? Then we have we are ready so to run the standard BFS. So basically val q, and then what we are going to do is we get the current status and the number of operations. So this is the q pop left, right? So notice that this pop left operation is O1 in time. So then first we are going to check if current equals the final status, right? So then I'm going to return the number of operations, right? So this is one. Then what I'm going to do is, so I'm going to pick a sublist and then take it out and put it in any position. In other words, construct the next state with one operation, right? So basically for L in range length current, actually this is the fixed number, right? So then what we have, then this is for L, for R in range, so L, and then length current. So in other words, its starting index is L and the ending index R. We can have empty sublist, but this will be already visited, right? So this is just some detail. Then the subarray we are going to think of is current from L to R. So we write R plus 1. And then the remaining one, after we get this, there will be current, so up to L, but not inclusive, plus current from R plus 1 to the end, right? So this is the remaining one, and this subarray. We can put this subarray in any place. So basically, for position in range length R, so we can put it in also the very end. So we plus 1 here, right? Then the new state will be R to the position plus the subarray, right? Then plus R, so position onwards, right? So then if tuple, the new state, not in visited, then we need to we can first check if new state equals B, right? So notice that this new state, this is a list, right? So here we are starting list, but if you don't want to distinguish, you can all make it a tuple, right? But this is just a small detail. So we are going to return the current number of operations plus 1, right? So otherwise, what we want to do, visited add the tuple of the new state, right? And then the q append this piece of information. So then what we want to add is a tuple, the new state in terms of a list, and then n operations plus 1, right? So if afterwards nothing has returned, you are going to return negative 1. See. So this is the full code for this problem. Let me test it. Yeah, it passes the 2 test cases. Now let's look at the generic case. Yeah, it passes all the generic cases. So here, let me make some comments. First comment. So we are sort of using brute force, but within BFS. The reason is that from the first constraint item, we know from a current state, we can construct all the next state within one edit and merge, right? This is exactly here what we are doing for L and for R, and then we pick it out and put it in any position, right? So this is the one thing. Another thing I want to comment is the data structure. So actually, if you do more coding, you will find that using proper data structure to solving problem is very crucial. So here, because we are using BFS, we are using Quill actually. So this is the second one. The third one is that for shortest path or distance problem. So here we are think of BFS. You can also think of Dijkstra's algorithm. So there are a number of problems in LeetCode involving Dijkstra's algorithm. So this is third comments. So lastly, maybe we have a YouTube channel, and within the channel we have a lot of playlists. So you can actually do some practice according to the problem type or the playlists. So with that said, I guess, thank you for watching. That's it.